everyone. My name is Junyi. I'm currently a newly joined faculty member at University of Michigan. Just joined a few months ago. And also just finished my first semester of teaching. Big relief. Before that, I completed my PhD at MIT just last year. So today I'm going to talk about our work around the regional health and medical monitoring systems that adapts to individual variances in the age of AI. So before we jump into the topic, what do I mean by regional here? So, let's first look at how the current personal health monitoring system looks like. No surprises. For example, like most commonly used smartwatches. You guys probably all own or at least see these flying around. Those things basically they're able to collect some of the health data for all users almost anywhere and anytime during the day, which is actually super great when you think about it. So these type of devices that can monitor what we call systemic biometric signals, such as heartbeat, blood pressures, as well as those behavior trackings. However, we as human beings, we're so much more complicated than that. We're just more complicated than two veins and plus a heart that pumping blood through the body. We actually have more stuff underneath. We also have what we call regional health conditions, such as muscle tissues, body fluid, organs, bones. The list goes on and on. Systemic monitorings that can record, for example, how many steps you took every day, and what's the corresponding heartbeat during those exercises, and then probably interpolate how many calories I do every day. However, during any of those activities, there's no way for those devices to know, for example, did I suffer from any regional muscle pains or unbalanced postures, or which can leads to the potential injuries, or how well did my lung functions during any of these exercises. So, why is it hard to monitor these regional health conditions with conventional devices that measures everyone? To start with, we are all, a little bit cheesy here, we are all unique and different. And we spot different body form factors with different health conditions, as well as different daily living environment. And to be a little bit more specific, we have different anatomical structural variances between different human subjects. As you can see in these two graphs, these are the CT image scan for the same neck C3 area for two different patients. They're quite visually different by just looking at them. And if you dive in, it's even more diverse from each other, such as, for example, on the top there, the skin boundary conditions and tissue component compositions are quite different across these two patients. For example, how much muscles versus fat you have in those areas. In addition, at the location-wise, some of the anatomical parts, such as the upper airway locations, are also quite different from each other, location and the shape of them. Even within the same human subject, each regional body part is different from each other. For example, if we were to measure the area around head versus neck versus waist, also the thigh areas, these are very different from each other, even if it's still within the same human body, and usually probably going to require some custom measurement setup and likely data processing models for different body regions to monitor those localized local health conditions. So as a quick summary here, compared to the systemic health monitoring, which can be captured from fixed locations across large population, regional health monitoring requires localized information, requires cross-sectional and sometimes volumetric informations of the target area, which is not quite feasible with conventional portable one-for-all health monitoring systems nowadays. Hence, requires more personalized systems. And what do I mean by that? Obviously, it's AI enabled, hence the title of the workshop. And to be more specific, I mean the personal and regional models and solvers that we built for each of these different applications and tasks. A little bit more background to tackle these personal regional body area monitoring. One of the sensing mechanisms that on the hardware side that we focused on is using electrochemical impedance sensing. This is one of the sensing board that we developed. It's still under active design iterations. I might get to talk a little bit more about this later on if I have time. But basically, for the impedance data we collected, one common technique for the researchers, including us, is to use EIT, or electrical impedance tomography, or EIS, basically electrical impedance spectroscopy. It's a similar, just at different frequency. Basically, it works as we measure the impedance boundary conditions around any of the regional body part. For example, in this picture, around like the thigh area. And based on the boundary conditions, we inverse solve for the internal impedance distributions at any of the given points, and use that to give like a cross-sectional, and we can do like 3D as well, or like volumetric image of the specific body regions. So some of the topics, some of the projects I'm going to hopefully quickly run through. First is the muscle engagement sensing for physical therapy treatments, in which we build the original models for the thigh area for the image solver. Second is the upper airway reconstruction for sleep apnea treatment, which we build specific patient-specific models for processing these obstruction data. And third, we probably don't have much time to get into, but real-time radiation monitoring for cancer treatment. This is mainly on the AI-accelerated hardware designs that's for essentially sensing super resolution. Essentially, we're trying to boost the sampling rate with the hardware board design to reach a much higher, 10 times or even 100 times sampling rate, effective sampling rate, based on an actual physically lower sampling rate. Yeah, like I said, probably only the first two. So on the first one, the muscle engagement monitoring. A little peek on the system we built, muscle rehab. It's essentially a muscle engagement monitoring and a motion tracking enhanced unsupervised remote rehabilitation system that it basically senses and visualizes the individual muscle groups around the thigh, and then also display it with your posture in real time. How do we actually sense this? This is like a quick demonstration on how the measurement setup goes. Basically, we have two arrays of the electrodes, 16 times 2, and then we wrap them around the upper thigh area. And for the data we collected, based on with the our custom sensing board, we built like a 3D volumetric data model here. And then to just make things a little bit more fancier compared to the traditional adjacent or opposite ways of measurement, we developed this we call SIG5, or basically like a combination of sensoring mechanism or sensoring setup that we capture both the cross-sectional and also the data across these two electrode arrays, have like a more balanced data around the whole area. And unlike the traditional inverse solvers, which basically usually start with a homogeneous distribution of the domain and then solve from that point, we built a custom forward model for the thigh area specifically, where we basically give the model information of where are the location to look at, what are the supposed value of each of these areas based on the muscle group locations, and then we assign those values to the model at the beginning, and to solve it from there instead of going from the very non-information at all, and then go step by step from there. And based on essentially different patient or different users, based on their BMI and body fat percentage, we custom assign each of these models to their sample area in order to have like a more accurate and also higher efficient real-time solve. This is just some image we did based on a phantom simulation, because we can't really cut open the human, and then just give you some ideas how this image reconstruction works with these custom regional models. And next is the patient-specific, which we use for the airway obstruction monitoring. So give you a little bit of background on the why do we do this upper airway monitoring. It's basically for this OSA, obstructive sleep apnea, which is a big issue. I'm not sure how many of you guys actually experience this, but basically up to 30% male, up to 15% female at some point might be experiencing this issues. And if it's severe, the surgery will be needed to help remove some of the blocking part around the upper airway to help ease the condition. However, there's not quite any of the anatomical location information that the surgeon know before they actually open you up, which is not great. So the current diagnosis gold standards for this OSA is called polysomnography, which is a sleep study. Basically, they wire you up with a bunch of electrodes and then do all those monitoring and then diagnosis whether you have it and also how severe it is. However, none of these current sensing mechanisms have anything around the anatomical blockage information. And what people do nowadays is actually called DISE, the drug-induced sleep endoscopy. Basically, how it works is, let me just show you a video. So basically, prepared. This is our brave collaborators from Children's Hospital, Colorado. So basically, you have the scopy go into your nose, and then you go just a little bit deeper, and then make a U-turn, and then go down towards your throat area. A little bit more. Okay, here we go. Then you get to see how the how these blocks, or like how essentially how your upper airway moves. So I hope this video convinces you that it's not quite pleasant for the patient, and it's definitely unfeasible for sleep study, which usually takes like 6 hours or so. Just imagine wearing that for 6 hours. And there's also like debates over effectiveness, but we don't have to get into all that. So what we proposed is a multi-frequency EIT neck gaiter, which is non-invasive, and then we custom designed those setup to fit the neck area. And I guess the most important or relevant part here is the patient-specific upper airway models we built. So instead of like the traditional way, or like even my previous way of solving the internal anatomical distribution inside, we basically built each patient a specific model based on their CT scans. And then instead of doing the raw data reconstruction around the entire data for the inside, okay, right there, we basically only look at the area that we interests us, which is the upper airway location. And because we don't have a lot of data for the actual models, we basically simulate all possible upper airway shapes around that location based on the guidance of the physician of different types of the obstruction. And then we use all these simulated data to build a custom patient-specific solvers, and then use that to cross-compare with the actual data we get from the patient and see how well they line up. This is like one of the earlier work we have. On the right is one of our collaborators who is doing the DICE, and then on the left is the data we captured that's constructed based on that. So hopefully they kind of aligned. And just to give you like a quick visual, we have the patient-specific models on the middle, ground truth on the bottom, and the top is the more conventional models that people use. So, okay, just a quick summary. Talk about the topics on the personal health and medical sensing systems that utilize the personal and regional models for the UMich solvers, basically, as well as, which I didn't get to talk to, but trust me, they're on the way, the AI-enabled hardware design, which is very much an ongoing work anyway. So, yeah. This is the topics I talked about. I have to confess here, the generated models like ChatGPT has not yet made into the core research of our research, except for the paper polishing. And you should totally see the faces of my collaborating medical doctors when I mention anything generative. So, but which brings down to like why I'm here, and actually one of the big reasons I'm here is I would love to learn more from you guys and to see how we can integrate these generative models to our regional health and medical monitoring applications. And yeah, with that, thank you so much. And if you have any questions or suggestions for how we can use these.
Okay.
So can you elaborate? Someone asking? We can go first.
Sorry. Yeah. Thanks for the exciting talk. I'm Arata from Zaran University. So you said that you're going in the future works you're gonna integrate ChatGPT or generative models into that. Okay. So actually, I'm wondering, so how it's like a possible, because So the current generative model is like data driven, and so they're so getting so many text or audio data from the web. So it's like regional monitoring. So it's pretty personal. The body structure is very personal, and it's kind of hard to get many data. So do you have some a way to avoid the data driven way or another a few shot something?
Yeah, that's a really good question. So as I mentioned, it's very much an ongoing process right now. I can share some of my early thoughts. For example, these simulated data that's on the upper airway only. This is like a very, very banana way of simulating different, essentially we just picked, say, I think we have like 4 different types of obstruction, and then we based on the widest that patient can open up, and then presumably was their smallest way of each of the reconstruction shape, and then we do like a linear interpolation between all those shape points, and then generate, I think, 5,000 shapes per condition for each patient. So this is like a very, very banana way of processing this, right? But if we use like a generative model to generate essentially not just that area, but hopefully the muscle area and other tissue areas that surrounds it, I think probably we can have like a much more accurate model for that patient, because the input data for the simulated model is essentially better. Or even better, if there are some underlying parameters that we are currently unknown of, we just simulate even millions of data points from across different patients based on however their CT scan looks like. Maybe we could have essentially, instead of like a patient-specific model, maybe we can have one model that fits for like a larger population. So this is one of the area I will really love to implement the generative models in, to have like a much better simulated data for our model. And the other thing is for the hardware design, I did not get to talk too much about this, but basically, can you see that? Okay, so basically what we're trying to do with our device is to sense those radiation effects during the radiotherapy treatment. But one of the big issues we have is those machines, the linear machines, they operate at such a high frequency. Also, the way it's, I think around like 6 gigahertz or so. Then that's like 10 times at least, 10 times to 100 times higher than any of the existing, like say STM microcontrollers, CPU clocks even. So one of the big challenges we're trying to work on is to have, how do we build like a model, build like a solver that can essentially use a lower sampling rate on the device that we can work with, but generate trying to essentially fill in the data gaps to have like a sensor data super resolution, so that we can essentially work with much higher sampling rate data. So that's also one of the area I really hope the generative model can do a much better job than however we're doing it right now. Yeah.
I have just saw that like a medical school has many like a CT data. Maybe you can make a foundational model for that.
Yes, that would be really great.
Thanks.
Thank you.
Oh, we're running out of time. I'm very
Yeah,
close to
we-
him. I
we
can
are-
ask
we
more
are running out of
questions
time.
in person. Yeah.
Okay, great then. Thank you. Thank you very much. Next we have Professor Junyi.